Hey guys, welcome back. In this video, we're going to look at one of the most powerful algorithms in computer science, the binary search. So to understand binary search, we're first going to look at an example where we search through an array of 9 elements. Now it is important to note that binary search will only work on an array that is already in order. And this calls to mind the importance of sorting in computer science, which we will look at a later date. In this array, we're going to look for the number 28. Now you can clearly see that that element is right here at index number 3. But we're going to start by not knowing where it is. So we set our target index to -1. And as you look at binary search, you're going to want to keep these two things clearly separated in your mind, the contents of the array versus the index number. It's also important to note that we do not want our algorithm to return 28. We want it to return 3. The binary search tells you where something is. You provided the number that you're looking for. Binary search starts by initializing 2 pointers, one called high and one called low. Some implementations call these pointers left and right, but that gets confusing when we start to explain what happens when these pointers move. Next, we initialize a pointer called mid or middle. This one is always the average between high and low, and so we add those two together and divide by 2 to find the middle point. Binary search starts by then asking the question, is your target less than what the contents of array mid contains? So in this example, we're asking, is 28 less than 33? Remember, we don't know where the 28 is, we're trying to find it. In this case, 28 is less than 33, and so we act in the following way. We know now that all of the numbers on the right of mid are not what we are looking for, because the array is sorted, and all numbers to the right of mid are greater than mid. And so we move the high pointer over to the left of the current location of mid. We know that our target, 28 in this case, is somewhere over here on the left. We then repeat the process. We reset mid to the average of high and low. Now, one nice consequence of integer truncation is that we don't have to worry about a 0.5 showing up. We ask the question again, is 28 less than 13 in this case? Remember, we always want to compare our target to the contents of the array. Now that's false. So we introduce an else-if clause in our pseudocode, where we ask, well, is 28 greater than 13? Of course, that is true. And so we react in a similar manner. We can now eliminate everything to the left of the current location of mid, because everything to the left of mid is less than our target, based on what our else-if has told us. In this case, we move low to the right of mid, and we continue looking. Now again, we calculate the average of low and high, which in this case resolves to the index number 2. Now, it's fine for this to happen. It's fine for mid to assume the same value as low, because the algorithm is going to work the same. Is 28 less than 19? No, it is not. Is 28 greater than 19? Well, yes, of course it is. And so we react by moving low to the right of mid. Recalculating again. Is 28 less than 28? No. Is 28 greater than 28? No. And so our final clause in our if statement is to check to see if that we actually equal the contents of the array at this location. If this is true, then we know that we have found our target, and this is the answer that we want our algorithm to return, mid. And so that's the complete binary search algorithm. We just keep repeating moving left, moving right, recalculating mid, until we have found our target. But how do we know when to stop the loop? Well, to illustrate this, I'm going to look for a different target. I'm going to look for a number that isn't in the array, 35. Let's see what happens when we go looking for a number that isn't there. Remember, we're looking for 35, and so this if statement is going to resolve to true. 35 is going to be less than 41, the current location of mid. And so according to that, our algorithm says to move high to the left of mid. And now we've arrived at our stopping condition. High is now less than low according to our algorithm. And this is kind of an impossibility, both from a logical sense, but also this is the signal to our algorithm that we have exhausted the array. We have looked everywhere that the binary search was meant to look. And now we have moved the pointers into locations that shouldn't exist. So there are two ways to stop the binary search. The first and the most important is if you find the target. Obviously, in that case, you want to return the index that you found. In the other case, if you ever move high less than the low pointer, or in some implementations they check if the low pointer is greater than the high pointer, then you know that you have not found the target, nor are you going to. And in that case, you would return -1. So that's the algorithm. Now let's take a look at some source code. So here you can see that I have written a short little main. I declare the array right here. It has the same numbers as you saw in the slides. And I go looking for 28 and 35. And I do that by calling a method that I've written called binary search that takes as its first parameter what I'm looking for and takes as the second parameter the array that I'm going to be looking through. So you can see that not much has changed from the pseudocode. I no longer need to declare a target variable because I'm passing that as a parameter right here. But I do need to declare that target index, set it to -1. And here's where I initialize low and high. And here is where I have set up my loop. Now this code is new. It was not in the pseudocode. It was my blue arrow basically. And you can see that I have set up both of our ending conditions in the while loop. The first one is look to see if target index is found or not. So right here I'm checking to see, keep going as long as we have not found anything. And keep going as long as high is greater than or equal to low. In other words, it's in its correct position. And do recall that sometimes high and low will stack on top of each other in the algorithm, so it is appropriate to say greater than or equal to. And the rest of it looks pretty much like the pseudocode. We go ahead and calculate mid right here. I did make one small change. As soon as we find the target, I go ahead and stop looking. So my first check for the if statement is to see if we have found our target. Otherwise, I check to see if we are less than or greater than. And then the loop will stop based on an ending condition if high crosses low inappropriately, or if we have found our target, and we simply return target index. Notice that target index was initialized to -1 up here, so if high and low cross paths, then we will simply return a -1. So binary search has a really pretty recursive implementation, and I have written that code here. This is my original binary search method where I pass it the target and I pass it the array. And it is simply going to return an answer from an overloaded binary search method, which still takes the target and the array, but now also takes the bounds that I want to be searching in. So there is a lower bound, and there is a high bound here. Initially, I will, of course, be passing a 0 and a length -1 as my bounds because I want to start searching through the entire array. Here is that recursive binary search method down here then. It takes a low and a high as its parameter. The first thing that it checks is that if high ever crosses low, it will return a -1. The next thing that it does is it calculates mid, because it needs to check the second base case down here if target equals mid. And it is possible that on the very first try we found target at mid, so that's why we have to check this or calculate this in between the two base cases. Finally, then we write our if statement. If target is less than array.mid, we call our recursive binary search again, but this time we are passing it parameters that define the left-hand side of the array. So this is low, i.e. 0, and here is mid -1. We have moved high over to the left of mid. Otherwise, we simply call binary search and look on the right-hand side of the array. So this time we move low to mid +1, and we keep our same upper bound. Running this code, you can see that it works just like the original iterative binary search. We found 28 at 3, we found 35 at -1. And I like this, this recursive algorithm because it's so pretty, and it clearly shows you searching on the left versus searching on the right without a bunch of extra variables thrown in. You know, binary search is such an important algorithm because it is extremely powerful. With a binary search, you can search through an array of 10 billion elements in about 30 passes of your loop. This is an incredible improvement over searching through those same 10 billion array elements with a linear search. On average, that would take you 5 billion passes in your array. So 5 billion versus the approximately 30, that's quite a savings. Anyway, I hope you enjoyed this presentation, and I look forward to seeing you next time.